Hello everyone. In the last lecture, we discussed three-phase star-connected network. For three-phase star-connected network, we define line voltage, phase voltage, line current, phase current, and we also derive the relationship between voltages and currents in three-phase star-connected network. Now let's see the second method of connecting three single-phase generators to generate three-phase power. This method is called delta connection or mesh connection, and the symbols are this triangle, that is delta or D connection. How can we have a delta connection? The dissimilar ends or different ends of the three-phase windings are connected together. For example, the starting end of one winding is connected with finishing end of next winding. Similarly, starting end of the second winding is connected with the finishing end of third winding, and starting end of third winding is connected with the finishing end of first winding. By connecting this type of dissimilar or different ends together, we will have a delta connection or mesh connection. So in the figure A, you can see the delta connection in which the R phase, Y phase and B phase, they are connected with each other. The starting end of R phase is connected with finishing end of Y phase. Starting end of Y phase is connected with finishing end of B phase, and starting end of B phase is connected with the finishing end of R phase. In this manner, we have a delta connection. So if we simplify the network, we will have the diagram like figure B. In this case, the induced currents are shown. In R phase it is IR, Y phase IY, and B phase it is IB. So let's assume this is a junction A, here there is a junction B, and there is a junction C. So what is happening at junction A? At junction A, current IR is entering and current IB is leaving. So as per sign convention of KCL, that is Kirchhoff's current law, the current entering is considered positive and the current leaving is considered negative. So we can apply the KCL at junction A, it is IR minus IB. Similarly, at junction B, current IY is entering, current IR is leaving. So the current in outer conductor is IY minus IR. And in the same way, at the junction C, current IB is entering and current IY is leaving. So the current in this outer conductor is IB minus IY. Now please note down here that this is not an algebraic sum or algebraic difference. This is a vector difference, because this IR, IY and IB are vector quantities, AC quantities. So this is KCL but vector difference. Now between different terminals, the induced EMFs are also shown in the diagram. For example, the induced EMF here, the induced EMF or the EMF measured between terminal R and terminal Y is VRY. The voltage between terminal R and terminal B is VBR, and voltage between terminals Y and B is VYB. So as we are measuring the voltage between two phases, between two lines, these voltages are called line voltages. So if you observe, the line voltage between terminal R and Y is VRY, and VRY is nothing but the potential difference between these 2 points. Let's say point A and point B. So what is potential between points A and B? It is nothing but EMF induced in R phase. So let's denote with ER. So this ER is phase voltage of R phase, and the same voltage is available between terminals R and Y as line voltage. In a similar way, let's consider terminal phase Y. In phase Y, let's say induced EMF is EY. So this EY is available between terminals B and C. Now the same voltage, same potential is also available between terminals Y and B, or terminals number 2 and 3. And what is the potential called between terminals Y and B? It is VYB. And VYB is nothing but line voltage. And the same thing is true for B phase. That whatever EMF is induced in B phase, the same EMF is available at outer terminals, terminal R and B, that is VBR. So in star connected network, the phase voltage is equal to line voltage. Phase voltage is equal to line voltage, but phase current is not equal to line current, because phase current in R phase is IR, but the line current in in conductor R or phase R is IR minus IB. Similarly, phase current of Y phase is IY, but the current outgoing is IY minus IR. So this IY minus IR, IB minus IY, IR minus IB, these currents are called line currents, and IR, IY and IB, they are known as the phase current. So let's derive the equation for line currents and phase current. One more thing we observe from the diagram is the star connected network is three-phase four-wire system. The star connected network is called a three-phase four-wire system, because three-phase wire and one neutral wire, total four conductors are there. In the delta, it is three-phase three-wire system. So the delta is called three-phase three-wire system. And why it is three-phase three-wire system? Because here there isn't any neutral. There isn't any common point where all the three phases are connected. So in delta connection, no neutral point. In the absence of neutral point, it is only three-phase three-wire system. So please remember, star connection is three-phase four-wire system. Delta connection is three-phase. Now, line voltage and phase voltage relation already we have discussed that in the in the delta connected network, the voltages between any pair of lines or any pair of terminals is equal to the EMF induced in the phase, that is called phase voltage. And because of line voltage is equal to phase voltage, here we have written VL is equal to V phase. So this VRY, VYB, VBR are line voltages, and it is denoted by VL, whereas ER, EY, EB, they are the induced EMF in the three phases, and line voltage is equal to phase voltage. Then the relation between line currents and phase currents. As we discussed earlier, that when we apply the KCL, Kirchhoff's current law, at all the three junctions, we will have a vector difference of two phase currents available as a line current. So we can write the current in line 1, let's give the name I1. I1 is nothing but IR minus IB. IR minus IB. Similarly, current in line 2 is IY minus IR, and current in line 3 is IB minus IY. So on right hand side, it is the difference of two phase currents. And the left hand side quantity I1, I2, I3 are line currents. We need to derive the equation, proper equation, so that we can calculate the value of line current if phase currents are given, and value of phase currents if line same as star connected network. If we draw the vector diagram, then VRY vector, this is VYB and VBR. All the three voltage vectors, whether you call it line voltage or phase voltage, they are 120 degree apart from each other, because this is perfectly a balanced three-phase system. So all the three voltages, whether you say line voltage or phase voltage, they are 120 degree apart from each other. In individual phase, the induced currents are IR, IY and IB. And as we discussed earlier also, that it is an inductive coil in which current lags behind voltage by some angle. This is not a perfectly pure inductor or pure coil. In a perfectly pure inductor or coil, current lags behind voltage by exactly 90 degree. But here, this phase current lags behind the phase voltage by degree phi, and phi is less than 90 degree. So IR lags behind VRY by 5 degree, IY lags behind VYB by 5 degree, and IB lags behind VBR by 5 degree. All the three current vectors are shown. Same as the voltage vectors, these phase currents are also 120 degree apart from each other. So the angle between IR and IY is 120 degree. The angle between IY and IB is 120 degree. And the angle between IB and IR is 120 degree. So not only voltages, but current also having the phase difference of 120 degree with respect to each other. Now, how can we calculate the line current I1, I2, I3? So what is I1? I1 we have written I1 vector is equal to IR vector minus IB vector. So you can see here IR vector is like this. Here this is IR vector and IB vector is somewhere here. And this is 120 degree phase. So IR minus IB means we have to take the minus IB. Minus IB means 180 degree apart from current position. So this is minus IB. Now if we calculate the resultant of these two vectors, this vector is I1. So in this diagram you can observe, you can see that vector difference of IR and IB or minus IB is this vector. So this is IR, this is minus IB, and it is nothing but IR minus IB, and it is denoted by I1 vector. Similarly, IY minus IR is IYR, IB minus IY is IB minus IY. And these three currents are the line currents. Now, the angle between IR and IB reversed. So IR and IB reverse is this. This angle is 60 degree. If IR is equal to IY, all the three windings are identical. So in all the three winding, same current is induced. So we can say IR is equal to IY and we can label it as I phase. Then the current in line number 1 is I1 is equal to 2 into I phase multiplied by cosine of angle between two phase current divided by 2. So angle is 60 degree. So cos 60 by 2. Cos 60 by 2 is cos 30. Cos 30 is root 3 by 2. 2 will be cancelled. We will get I1 is equal to root 3 I phase. Now I1 is line current. So we can write IL is equal to root 3 I phase. For remaining two line currents I2 and I3, the similar equation will be applied. because it is a perfectly symmetrical system. In short, we can write I1, I2, I3 is equal to IL, and the final relation in three-phase delta connected network is IL is equal to root 3 I phase. From the vector diagram, it should be noted that the line currents are 120 degree apart. So all the three line currents I1, I2, I3 are 120 degree apart from each other. That is, angle between I1 and I2 is 120 degree, between I2 and I3 is 120 degree, and between I3 and I1 is also 120 degree. Phase currents also 120 degree apart from each other. Phase voltage and line voltages are also 120 degree apart from each other. The line currents are 30 degree behind their respective phase current. So that is visible from the vector diagram. The angle between line currents and the corresponding line voltage is 30 plus 5 with current lagging. So current lags behind, line current lags behind the line voltage by 30 plus 5. If we compare this relationship of star connection with delta connection, three-phase star and three-phase delta connection, then in three-phase star connection, VL is equal to root 3 V phase, whereas in delta connection, VL is equal to V phase. This is voltage relation in star and delta. What is current relation? Current relation is in star network, IL is equal to I phase, whereas in delta connection, IL is equal to root 3 I phase. So this is the relationship between voltage and current in three-phase star and delta connected network. Now let's derive the equation for power in three-phase delta connection. So the power in three-phase delta connection is given by total power is equal to 3 multiplied by phase power. Phase power means power generated in any phase. As all the three phases are identical in nature, they have same winding, they cut the same amount of magnetic flux, same amount of power will be generated in all the three phases. So the total power, total active power or true power is 3 into phase power. We can write the equation for phase power. So the total power P is equal to 3 multiplied by phase power is nothing but VPH IPH cos phi. Now in place of VPH IPH, we can put the relationship of voltage and currents, and we know that V phase is equal to VL and I phase is equal to IL upon root 3. So put these two values in this equation. So we will get P is equal to root 3 VL IL cos phi. This is in watt, power in watt. So the total power of three-phase network, three-phase circuit is root 3 VLIL cos phi. If you recall, the total power induced in three-phase star connected network, the equation was similar, root 3 VLIL cos phi. So whether it is star connected network or delta connected network, the total power in the circuit is given by the equation root 3 VLIL cos phi. It is same, root 3 VLIL cos phi. Now our last point, last topic of this chapter is power measurement in three-phase circuit. How can we measure the power in three-phase circuit? Following methods are used for measuring power in three-phase load or three-phase circuit. First method is 1 wattmeter method. Second method is 3 wattmeter method, and third method is 2 wattmeter method. Now we know what is wattmeter. It is the device equipment used to measure the power, and the symbol of wattmeter is this. We have discussed in the first experiment. This is wattmeter and the terminals are M, L, C, V. Now in wattmeter, this coil is known as CC and this coil is known as either PC or VC. PC is potential coil or voltage coil and CC is called current coil. Now how can we connect the wattmeter? Let's assume here there is a source and here there is a load, and we would like to measure the power consumed by this load when connected across the source. Then we can connect the wattmeter like this. Current coil is connected in series, potential coil or voltage coil is connected in parallel or across the load. So the CC will measure current, PC will measure voltage, and this is the method of connecting wattmeter in the circuit. Now let's see these three methods to measure the three-phase power in three-phase circuit. 1 wattmeter method. This 1 wattmeter method, as name suggests, only 1 wattmeter is used, and this method is used only in a balanced three-phase load, when the load is perfectly balanced. What is the meaning of perfectly balanced load? Let's say we have a star connected load like this. So this is R phase, Y phase and B phase. It is Z1, Z2 and Z3. These three are the impedances. So balanced three-phase load means all the three impedances are same in magnitude. That is Z1 is equal to Z2 is equal to Z3, and all the three phases are having same power factor. That means cos phi 1 is equal to cos phi 2 is equal to cos phi 3. This is the definition of three-phase load, balanced three-phase load. Balanced three-phase load means the magnitudes of impedances are same and their power factor is also same. If the magnitude of impedances and power factor are same, all the three phases will consume same amount of power. And when phases consume the same amount of power, we can measure the power of any one phase. Let's say we connect the wattmeter across R phase only, and we measure W1, for example, W1 of R phase. To calculate the total power, we need to multiply this reading W1 by 3. So the total power consumed by this perfectly balanced three-phase load is 3 into measurement of that single wattmeter. So this is called 1 wattmeter method. Advantage is only 1 wattmeter is used. So cheaper method occupies less space, easier to use and so on. But the disadvantages are it can be used only in perfectly balanced three-phase load. If the three-phase loads are not balanced, all the three phases are not having same impedance, we cannot use this method. So this is 1 wattmeter method. Next, 3 wattmeter method. If we have three-phase load, either star connected or delta connected, and all the three phases are having a different impedance, that means the load is not three-phase balanced load but three-phase unbalanced load. In that case, all the three phase will consume different amount of power. So we cannot use single wattmeter method or 1 wattmeter method. In that case, we have to connect 3 wattmeters in all the three phases. and the method is called 3 wattmeter method. So here in the diagram you can see 3 wattmeters are connected. In figure A it is delta connected network, figure B it is star connected network, and W1, W2, W3 are 3 wattmeters. So the CC current coils are connected in series with the phase, and pressure coils are connected across L1, L2 and L3. Similarly in star connection also, current coils are connected in series with the line, and pressure coil or voltage coil is connected between phase and neutral conductor. That means across the L1, L2 and L3. So here 3 wattmeters are used. How can we calculate the total power? Power here in that 3 wattmeter method is W is equal to W1 plus W2 plus W3. So summation of all the 3 wattmeter readings will give total power W. Third method is 2 wattmeter method. Now if you compare 1 wattmeter and 3 wattmeter method, 1 wattmeter method is used only for balance load, 3 wattmeter method is used only for unbalanced load, or it can be used for balanced load also, but it is costlier because we need 3 wattmeters. So method is costlier, uh, occupies more space and so on. So we have to optimize, and it is the 2 wattmeter method. In this method, as the name suggests, only 2 wattmeters are connected or inserted in any two lines, and the potential coils of each wattmeter is connected to the third line. So let's see the diagram. You can see in the figure A, it is delta connected network, W1 and W2, 2 wattmeters. W1 is connected, its current coil is connected in R phase, and its pressure coil, this pressure coil is connected between R phase and B phase. Similarly W2, current coil is connected in Y phase, and the pressure coil is connected between Y phase and B phase. In 3-phase star connected network, here we have not used the neutral conductor. The W1 current coil is connected in R phase, and its pressure coil is connected between R phase and B phase. W2 CC or current coil is connected in Y phase, and the pressure coil is connected between Y phase and B phase. So the connections of both the wattmeters are different compared to 3 wattmeter method. Current coils are connected in two phases or two lines, and their uh, PC or voltage coil, it is connected to the third remaining phase, that is B phase. Now from the diagram you can see that the current coil of wattmeter 1 will measure this line current of R line. Current coil of W2 will measure current of Y phase or Y line. Pressure coil of W1 measures the voltage between R and B. So this will measure VRB. Pressure coil of W2 will measure VYB. Similarly in star connection also, this pressure coil will measure the line voltage VRB, and this will measure VYB. The current coils, this will measure IR, and this in this case this will measure IY. So looking to which quantity the W1 and W2 current coil and pressure coil are measuring, we can calculate the total power consumed by these three. For example, let's say instantaneous current through W1 is IR in delta connected load. Instantaneous potential difference or voltage across W1 is ERB. It is nothing but ER minus EB. Similarly, instantaneous power measured by W1, this product of voltage and current. So it is IR into ERB. ERB is nothing but ER minus EB. Similarly for W2, the current through W2 is IY. Potential measured by W2 is EYB. It is nothing but EY minus EB. And the power measured by W2 is IY into EY minus EB. Now what is the total power? Total power is W1 plus W2. So here W1 plus W2, it is nothing but IR into ER plus IY into EY plus IB into EB. This is nothing but IR into ER is power consumed by R phase. You can see ER is potential across R phase, IR is current of R phase. So IR into ER is power consumed by R phase. Similarly, power consumed by Y phase, power consumed by B phase. And we can write it is P1 plus P2 plus P3. Now on left hand side, we can put the values of W1 and W2. So W1 is this IR into ER minus EB. W2 is this IY into EY minus EB. And we can draw the vector diagram for balanced load. So let VR, VY and VB are the RMS values of three-phase voltages, and IR, IY and IB are the RMS values of three currents. So you can see here, this is VR at 120 degree, VY at 120 degree, VB. Now current IR, IY and IB lags behind the respective voltages by 5 degree. Now what is line voltage? It is VR and VB, a vector difference of VR and VB. So VR and VB vector difference is VRB. This is line voltage. Similarly, another line voltage where wattmeter 2 is connected between phase Y and B, it is VY minus VB. So we will get VYB. So this is another line voltage measured by W2. The respective currents measured is IR and IY. So they can be expressed by vectors as seen in the diagram. The current through wattmeter W1 is IR. Potential difference is VR minus VB. That is the vector difference. And from the vector diagram, just refer to the vector diagram, and it is seen that the phase difference between VRB and IR, that is line voltage and line current, is 30 minus 5. So the reading of wattmeter 1 W1 is IR into VRB into cosine of 30 minus 5. Now recall, what is the equation of active power? VI cos phi. Phi is the angle between voltage and current vector. So IR is current, VRB is the this is line current, this is line voltage, and the angle between these two line this voltage and current vector is 30 minus phi. Similarly for W2, W2 current is IY, voltage measured is VYB, and the angle between these two, this current and voltage is 30 plus phi. Just go through the vector diagram. you will find that this angle is 30 plus 5 degree. And power equation we can write W2 is equal to Iy into Vyb into cos 30 plus 5. Since the load is balanced, this VRY, VYB can be termed as VL, IRIY can be termed as IL. So in both the equations we can replace this VL IL and we will have a final equation VL IL cos 30 minus pi, VL IL cos 30 plus pi. And if you add these two, we will get the total power, that is W1 plus W2. So VLIL cos 30 minus pi plus VLIL cos 30 minus pi and 30 plus pi. VLIL common, we will have cos 30 minus pi into cos 30 plus pi. It is nothing but 2 cos 30 cos pi. Put the value of cos 30, it is root 3 by 2, 2 cancel. So root 3 VLIL cos pi. So here total power consumed, let's say it is W, is root 3 VLIL cos pi in 3-phase delta connected network. In the same way, you can prove the power measured by 2 wattmeter methods in 3-phase star connected network, 3-phase star connected balanced network. It is root 3 VLIL cos pi. Same method you can follow. Now, not only we can measure the power with the help of 2 wattmeter methods, but we can also calculate power factor of this load. If it is a balanced load, then the total power is W1 plus W2, which is root 3 VLIL cos pi. If we take the difference of two reading, this is summation of two reading. If we take the difference of two reading, W1 minus W2, we will get VLIL sin phi. And if we divide equation 2 by equation 1, that is if we take the ratio of W1 minus W2 divided by W1 plus W2, then we will have tan phi is equal to root 3 W1 minus W2 divided by W1 plus W2. So this is W1 minus W2, this is W1 plus W2, and W1 W2 are the two readings of wattmeter. From this equation we can calculate phi, that is phi is equal to tan inverse root 3 W1 minus W2 upon W1 plus W2. If you take the cosine of the phi, you can calculate the power factor of the circuit. This is for balanced load. If further, we may express the power factor in terms of ratio of the two wattmeter readings. For example, smaller reading is W2. Why W2 is smaller reading? Because W2 reading is root 3 VLIL cos 30 plus pi, and W1 reading is cos 30 minus pi. As this cos 30 plus pi angle is greater than 30 minus pi, the cosine value will be smaller in this case. So W2 reading is smaller than W1 reading. So if we take the ratio smaller reading to larger reading, so W2 divided by W1, we give the name R. This ratio is R. Then from the equation 3, that is tan phi is equal to root 3 W1 minus W1 minus W2 divided by W1 plus W2. From that equation, we can rearrange like root 3 1 minus W2 upon W1, 1 plus W2 upon W1. In place of W2 divided by W1, put R. So the equation becomes root 3 1 minus R divided by 1 plus R. We know that sec square phi is equal to 1 plus tan square phi, or 1 upon cos square phi is equal to 1 plus tan square phi. So we can use this a trigonometric and derive the equation for cos phi. So the cos phi is equal to 1 plus r divided by 2 into 1 minus r plus r square, where r is the ratio of smaller reading of wattmeter to larger reading of wattmeter. And if we plot the value of r against cos phi, then we will have this kind of curve. So on x-axis we take power factor starting from 0 to 1. On y-axis it is the ratio of W2 by W1, and we will get this type of curve which is known as watt ratio curve. So from this, if we know this ratio, let's say it is 0.4, then for 0.4 we can calculate the power factor readily. We can measure the power factor readily. So this is power measurement and power factor measurement in three-phase circuit. For this chapter, AC circuit, you may refer the book B.L. Theraja, Electrical Technology Part 1 and 2, and other material. So this is the end of chapter number 2, AC circuit.